Very, very honored to be here today. I want to thank you guys for all the work that you do. This is sustainability and climate change is definitely a big thing that's very dear to my heart, and why I accepted to come here today. I accepted the invitation, so thank you. I'll cover a few things this afternoon. Exascale, how we got here. I think it's important, especially with a community that's not aware, is that Exascale was not a walk in the park. So as we build the next generation superscale system, it's important to understand how we got there. I'll try to get you guys to dream a little bit about what systems could we bring, even with today's technology, and then you can bridge into what we could have in a few years from now. How AI could help, very few slides on that. And ultimately, how we deliver on limiting the carbon footprint of those massive build-outs. Because when we're starting, during the Exascale program, we thought that I really thought the limit would be at 25 to 30 megawatts per supercomputer, but now we're really thinking to go maybe even 10x that in some future builds. So how can we build those supercomputers in the most sustainable way beyond the benefit they provide? We want to make sure their energy consumption also is really done the most efficient way possible. So Exascale and how we got there. We achieved Exascale on May 27th, about a year ago, at 6:16 in the morning. I will remember that date and time my whole life, having worked on that for 10 years. I joke around because I know I have two boys. I know one was born in the evening, and one was born in the morning, although don't ask me about the time. But I will remember that we hit Exascale at 6:15 in the morning on that Friday morning. Frontier is a massive system. It's 74 racks. It's nearly 40,000 GPUs. It hit 1.102 exaflop. That was when we actually first hit it. They just got a new benchmark in. They're just below 1.2. It's 19.2 petaflops per rack. So by itself, each rack would take several places in the top 50. It's got massive memory, massive injection bandwidth. And what you see down there, this is what we call the tail of an impact run. So as we're following the system as it's running the run, this is towards the tail of it. And this is one of the most nerve-wracking spectator sport for geeks, because you never know if the run will complete. You got to realize running in a system this scale, you're running into resiliency, into reliability aspects that Jensen talked about miracles this morning when the folks at DOE and at the big wigs at HP were asking me about this. They're like, hey, are you guys going to make it? I'm like, guys, we didn't. They were like, you pulled off a miracle. I'm like, you don't understand. Many people are religious in the world, therefore they believe in miracles. This was a statistical impossibility. To get a system this scale to run for 4 hours or more now, and Satoshi reports the same thing on Fugaku, to get those systems to a state of stability and cleanliness such that it can run for several hours on tens of thousands of GPUs is quite an engineering feat. So we're super happy about that. And it happened because we had it was almost a decade of R&D prior to actually building the system. Hewlett Packard Enterprise acquired Cray a few years ago, and we had two parallel programs that accelerated the investment in photonics, in liquid cooling, in chip architecture, and routing. And now the whole community, the broader HPC community, and AI, as you'll see in a few minutes, benefits from that. But as we think about the next generation of systems and really building large systems, we have to remind ourselves that those are not like engineering free. Building very large systems come with, like we're talking about building a next generation Earth simulator, right? Or something that will have very fine granularity and precision in the grid that it's able to simulate. So for that, we really need to engineer the system to do that, and we need to be conscious about how to design it and about driving the R&D that will actually deliver the outcome. So where could we go next? I'm going to cover two options. And just to get you guys thinking, to get you guys calibrated a little bit on what it could look like. So I kind of picked up some of my and my team's work on the Exascale system design. What you see depicted here is a 200, it's kind of a notional system design. Don't go to your HP or NVIDIA sales rep to ask for this. It's just to get you guys kind of the ballpark of what it could look like. It's 256 racks. You could have 64K GPUs, or 65,536 GPUs. And I've drawn it as a 3D HyperX, which is a type network that's fully connected. It's a generalized Dragonfly for those of you that are kind of geeky in computer architecture. That system using, let's say we use the NVIDIA H100, with Jensen speaking this morning, which is the fastest GPU on the market today. We'd have 2.2 exaflops in FP64 SIMD. If we're using the tensor cores, it would double. What's interesting is on BFlop 16, which we use on AI, that would be 130 exaflops peak. Quite a bit of memory bandwidth. The power would be in the ballpark of 60 to 80 megawatts. Again, it's just to give you guys broad order of magnitude. The floor space would be 1,000 square meters, and it's few $billion. And there, please don't quote me on that. It's just to give you an order of calibration on how those systems may cost once you include the storage file system, some of the facility build out required, obviously the system costs and all of that. So that's kind of ballpark what that system could look like. So that's one option. There's actually a way to build even bigger than that, and by exploiting basically the NUMA domain of 8 GPUs, you can actually build an 8-rail version of this. So I call that the option 1 XL. And that then multiplies pretty much everything by 8. That system's now, you can read all of the specs. We're over 500,000 GPUs. That would definitely drive the NVIDIA stock even better, I'm sure. What's interesting is that it's now 8,000 square meters, right? So that's bigger than a football field. And by football field, I mean European football, not American football, like you guys would say here, real football. And it would be in the tens of billions of dollars. So people are going, oh my God, this is super expensive. But if you put that in perspective, right, at CERN and many other big instruments, CERN's now looking at building a $23 billion 100-kilometer particle accelerator. And yet, I mean, this is fundamental science, right? This is for understanding the Higgs boson and all of that and the origin of life. This is all great. But what you guys are doing is to actually preserve life on planet Earth. So I think as a community, you should allow yourself to ask just as much for building very large computers, because this is much more of an existential crisis for humanity than understanding the Higgs particle. So I wanted to do that. I kind of wanted to test what kind of ballpark we'd be if we were to dream big and really big something like supermassive. So that's one option. Option 2, and oh, by the way, you'll see you'll see the option 1 and 2 are actually not mutually exclusive. I think both need to play out. The way we're thinking about the post-exascale view at HP is really about federating constellation of systems. We call that how we accelerate workflows, or having multiple systems that are connected together, flowing data in real time, and really distributing the processing between, it could be pre-processing using DSPs, for instance, from large radio telescopes, radars and various sources. And then you pre-process, then you send it out, then it gets pre-analyzed, then there's a simulation supercomputer that's doing some other transformation on it, and then you have AI that's going to make inference. And all of that's connected and could be disjoint, not located in the same site, but all working together. By the way, there's a lot of work and there's a lot of engineering that needs to go into that. So this is one kind of high-level representation of our workflow, where you could have data coming from satellites, from wind sensors, from wind turbines. All of that can go into a simulation. You can have an AI surrogate model that would do simulation steering. It then feeds into live monitoring engines where you're looking at all of that data feeding in. And then ideally, you can have humans making live decisions on this. For instance, how to optimize a whole wind farm, depending on the weather. But you could also have an AI trained to do some of the same thing. And there's all various ways to have the workflow kind of re-enter and steer some of the calculations. And even in this case, I mean, going back to Satoshi's talk, I mean, eventually we might even be able to steer the weather. I don't know if you guys know, but not until not so long ago, Vail Resorts would actually seed clouds at Vail. Some of you might know that. So this is something that's not so far away. So what comes after exascale, and for many of us, it's going to be from edge to exascale. It's about coupling the usage model for our supercomputers today. It's like log in, upload your data, run your codes, run your apps, get your results, then go out. The future, we see a lot more connected. With edge, that could be, as I said, ground sensors, satellites, ocean sensors, and all of that feeding in real time. We need to democratize the parallel runtime environments. HPC is really constructed on MPI codes, OpenMP, but the new generation, and I'd be curious with this community, the new generation is really coming in wanting to use Jupyter notebooks. A lot of them use Python, and we as an HPC community need to be more listening and really empowering the whole new generation that's coming with a whole new set of tools. Performance portability is key because as we go into this next phase, and we're limited by the fab process to some extent, we're going to have a lot of specialized silicon. So it's important to have codes that can port. Many of the codes were built on CPUs. It's important to be able to port them on GPUs, but maybe also eventually on specialized AI accelerators. Yeah, you must be aware there's a ton of AI startups that are building custom chips for AI, especially in the inference space. Secure networking foundation. In HPC, our networks are not so secure. They're meant to be fast, but once you're in the circle of trust, really everybody can pretty much, it's kind of one big happy family. As we get into a place where we're connected to the edge, we need to have end-to-end encryption. We really need to think about our networks in a different way. Silicon innovation, kind of coupled with my previous point on portability, we need to enable those startups to come in with new silicon and provide them with a software stack so they don't have to build all of that from themselves. Hybrid execution pipelines, where we're going to connect CPUs with GPUs, where we're going to connect the simulation with the AI training or the AI inference. The worldwide data web, and there were some thoughts about that this morning. Think about how Google revolutionized the web compared to how it was before with Alta Vista or other providers. It basically indexed the whole thing, and then everybody got access to the content. Imagine if we had a way one day to be able to index the data and tag the data so people would be able to search it. Some of that happened during COVID times where data got shared a whole lot easily and a whole lot faster, and we were able to accelerate research a ton faster. So I think we have to get into a mindset, and I don't know how this community is, but across many scientific communities, where we can share data more easily, but in order to do that, we'll have to have automatic data tagging and indexing for people to search for it. And last but not least, what's really key to a bunch of us at HP is to design a system that's open, where there's full-on data sovereignty, the data is not locked in, there's no egress fees for pulling your data off the cloud or that architecture. And how we've called that, some of us at HP were asked to write a paper for the 75th anniversary of the IEEE Computing Society about the future of HPC. And we started doing that. We were looking, 400, 800 gigabit networking and the evolution of processors and GPUs. And ultimately, after some time, we're like, no, sure, we'll get that, but that's incremental. Really, the future of HPC, it's about federating supercomputers to work together to solve bigger problems in real time. And so I was talking to Rick Stevens, a friend of mine who's the director at Oregon National Labs. He's like, Nick, yeah, that's great, but we need to go sell that to Congress. We need to go sell that to the funding bodies around the world, and we cannot sell alphabet soup. We need to find a name for it. So we're kind of noodling on this, like, yeah, the future is really not about the Internet of Things. It's about the Internet of workflows, if you think about it. The Internet of Things is about having multiple things that have all IP addresses, but ultimately having your refrigerator that knows that you haven't had dinner at 6 p.m. and therefore you get a McDonald's ad for a burger is doesn't solve world's hunger, right? But having supercomputers running together, truly running complex workflows in real time is really what we want. So we kind of wrote a paper about that. It's kind of a high vision. I think it connects with a lot of the dots that I've heard this morning, so might be of interest. So for both options, whether we go big or go broad, there's R&D required. On the first scale, reliability and resilience at scale. On the first option, reliability and resilience at scale is not trivial, and we need to keep investing into that. Resilience between sites, how a site can take over for another one, depending, for instance, on adverse weather conditions. That's also something that we kind of have technology to do, but that needs to be done better and done more stronger. Data movement across site or to a single site. Again, we can learn some of what was done at CERN. How do we schedule between sites, optical networking, and really, I think one thing we need to start looking at a lot more it kind of gets geeky, but it's asynchronous runtimes. MPI is built as a runtime that's very synchronous. A lot of these workloads, especially in AI, we need to double down on the R&D for asynchronous runtimes, and that will be good for both the go big and the go broad option. So, will AI come to the rescue? So this is a simulation that was done in partnership with NCAR on a tool that's called SmartSim. What SmartSim does, it's an AI engine that's coupled in real time with the classical HPC simulation. And what it's doing, and it's modeling the eddy kinetic energy, and I could probably get a course from all of you guys on that. I'm not an expert. But what I understand from the team is that by using SmartSim in real time, the AI is able to steer the simulation to apply more precision, like around the equator and on the places of the simulation where there's actually action happening. So to get to that model using SmartSim, it took about 1/10 of the compute cycles that we would have used just doing it in the classical way, in the classical HPC way. So, AI, where are we at? What we've plotted here is the AI models that we had in what we call the first age, pre-deep learning. Then deep learning really had an explosion of new models. And what you see there is the compute, on the y-axis, the compute intensity of these. And now as we're running with generative AI in the foundational model, we're in a completely different space. To give you an idea, we now have, when we're starting to talk about GPT-4 and the likes, we're now beyond the flops or the computational intensity of a full week on Frontier. So those are big workloads, and now they're, people don't always realize that AI has come to supercomputing. They're strong scaling workloads. They need supercomputers to run. So the path to sustainable computing, I don't know if you saw that quote, but training ChatGPT, which is about 175 billion parameters, consumed 1,287 megawatt hours of electricity, or the equivalent of 552 tons of carbon dioxide. That was in a paper that was published some time ago. How do we make that more sustainable? We've announced at HPE, it kind of went public 2 weeks ago, our supercomputing cloud. By intent, we're rolling out a cloud that will be carbon neutral. Now, is that all empty words? No, because the first two sites we've selected, the first one is in Quebec, the second one is going to be in Northern Europe. That site can power over 100 megawatts. It's a 100% renewable grid. And when I say that, it's really important because there are many places in the world where you can buy like green electrons by paying a little bit more, but there's no such thing as electron routing on an electrical grid. The only thing you're doing there is that if that grid is 50% renewable, 50% non-renewable, if you're doing that, you're just pushing more of the green electrons to you, in theory, because none of that's happening in practice, forcing the consumer space and the industrial space to consume more the non-renewable electrons. And really what's happening is on a lot of these grids, the renewable power is limited because it's wind or something like that. So really what's happening there if you're building large supercomputing centers on those grids, you're likely just burning more coal or being less sustainable. So for us, selecting locations with 100% renewable grids means that there's no greenwashing of electrons in what we're doing here. So for us, that's essential. Thanks to direct liquid cooling of our systems, we're also able to run year-round with free cooling. That means that we do not require compressors to cool our systems. That means we're a whole lot more energy efficient on a year-round basis. And last but not least, we're recapturing the heat because we're generating hot water to those greenhouses that you see in the back in order to grow crops and actually offset. That's actually ends up being a carbon offset initiative. So that's my last slide, Torsten. So I'll leave you with an interesting math exercise. How many tomatoes can ChatGPT grow? Okay, so you'll have to follow me. I'll go fast on that. There's quite a few math, but it's not complicated math. A typical 500 square meters greenhouse in Quebec, Canada, will require, there's about 5,549 climate hours in that location below 10 degrees C. You're probably the first audience, by the way, that knows what a climate hour is and psychrometric chart and everything, so that's awesome. And great to talk to you guys about that. It's about 1,000 gigajoules per heating season. So if we take the 1287 megawatt hour, we convert that, that's with the factor of 3600, that's 4,633 gigajoules. So it's a ChatGPT running at that power energy consumption. It's about 4.6 greenhouses for 1 year. Now, the great thing about that, and there's more math I could show you, if anyone wants to see detailed math, I could show you that. Every greenhouse normally gets heated by natural gas. Will consume about 67 would produce about 67 tons of CO2 per year. So by already offsetting the gas consumption that would be used for heating the greenhouse, and by using the waste heat for the computer, we're already offsetting 310 tons or 67 cars of annual carbon footprint. And that's just for training GPT-3 once. So you can see we can do a whole lot more than that. So the tomato production math, it's about 75 kilo per square meter per year. Let's say 50% of the greenhouse areas for production, follow the math. We can produce 86,000 and some kilogram tomatoes per year. So I didn't know how much, honestly, a kilo of tomato was. So before coming here, I had to go to the grocery store. That's a picture I took. This is precisely 1 kilogram of tomatoes. It's about 8 nice, good-looking tomatoes. So you do the math, training ChatGPT or GPT-3 that's behind ChatGPT on the energy consumption equivalent to that. If you're doing it the right way and you're doing waste heat reuse, you can produce nearly 700,000 tomatoes per year. And with that, thank you very much.